Welcome to EE206 Circuits 1, Lecture number 3, Resistors in Series and Parallel. Now the goal in this lecture is, when you have a resistor circuit, how do you simplify it into a net resistance? To do that, it depends how the resistors are set up. They could be in series or in parallel. For example, let's start with resistors in series. Here I've got three resistors placed back to back. Series just means that the current through R1 has to go through R2. The same current has to go through R3. If the current doesn't split, each current is identical, that's in series. When you have resistors in series, the voltage adds, and you can see that. If I do the current loop equation, I get minus Vn equals V1 plus V2 plus V3, or bring the Vn left. Vn is V1 plus V2 plus V3. From V equals IR. The current I times R1 plus I times R2 plus I times R3 is Vn. Pull the I outside and I get the net resistance then is just R1 plus R2 plus R3. That's resistors in series, they add. A couple examples. Suppose R1 is 100 ohms, 200 ohms, and 300 ohms. The net resistance is 600. Or going the other way around, if I know the total is 1,000 ohms, and I've got 100, 200, that means R3 has to be 700 ohms. So in series they add. How about parallel? In parallel, the currents add up. So IN, conservation current, IN is equal to I1 plus I2 plus I3. From V equals IR, I know that the current I1 is Vn over R1 plus Vn over R2 plus Vn over R3. All that together has to be IN. So if I factor out the Vn, and from V equals IR, bring this left, I get Vn is IN times the inverse of R1 plus the inverse of R2 plus the inverse of R3. That's the net resistance. Resistors in parallel add, but this is where it gets kind of odd. They add as the sum of the inverses inverted. So in parallel, it's 1 over R that adds. In series, it's the R that adds. As an example, suppose I've got 100 ohms, 200, and 300. In parallel, what that's going to be is 1 over 100 plus 1 over 200 plus 1 over 300. Add that all up. Now take the inverse. And part of the reason to see for the inverse is this is 1 over ohms. To get ohms back, I've got to take the inverse a second time. The total is 54 ohms. Now note that in series, the resistance goes up. If I have 100, 200, and 300 in series, the total's got to be bigger than 300. In parallel, the resistance goes down. So if I have 100, 200, 300 in parallel, the total resistance is less than 100. It's 54 ohms in this case. I can also go backwards. If I measure the resistance and find out that the total is 100 ohms, and I know R2 and I know R3, find R1. There again, what I do is the net resistance is the sum of the inverses inverted. It's a little bit easier if I invert both sides. So I get 1 over the R net is 1 over R1 plus 1 over R2 plus 1 over R3. Solving, I get R1 is 600 ohms. And as kind of a sidelight, this is where the HP calculators are really nice. This is an app on a cell phone called Free42. It's an HP42 calculator that's $500 on eBay. It's a free app on your cell phone. With the HPs, calculations like this are really easy. To add 100, 200, and 300 in series, I add, which would be 100, and HPs use a stack. So I got to push that on the stack, input the second number. Now when I add, X and Y get added together. 100 plus 200 is 300. I push 300 on the stack, add that together. The total is 600. So 100 plus 200 plus 300 in series is 600. In parallel, it's take the first resistance, 100 inverse, 200 inverse. Now the inverses add, 300 inverse. That's 1 over R total. Take the inverse, that's 54.5 ohms. And the way you write in parallel is 100 in parallel with 200 in parallel with 300. Now with series and parallel, I can now simplify circuits. For example, if I have this circuit, I want to find out what is the net resistance seen by the 12-volt source. To do that, I collapse everything from the right. I've got 40 in series with 25, gives me 65 ohms. 65 is in parallel with 15, gives me 12.19 ohms. 12.19 in series with 30 gives me 42.19. I now redraw the circuit. 42.19 in parallel with 5 is 4.47. 4.47 in series with 20 is 24.47. So the total resistance is 24.47. Now let's go back and do that with an HP calculator, kind of show you how this works. With the HP, bring this back on the screen. What I would do is take 25 in series with 40, 25 enter 40 plus, and parallel with 15. Take that inverse, 15 inverse plus, take the inverse. That's 12.19 ohms. So that's everything through here. Now in series with 30, gives you 42.19. In parallel with 5, in parallel the inverses add, so the inverse of 42, inverse of 5, inverse, add the inverses, take the inverse, that's now 4.47 ohms. Plus 20 gives you 24.47. So the HPs make calculations like this really, really easy. Another way to check your answer is to throw it in Circuit Lab. So if I take Circuit Lab and put in the voltage source, the resistors, just using drag and drop, I then connect the components together. Here's my circuit. And note when you build your circuit, I should have little dots at these points. The dots means there's a connection. If you don't see a dot, that means it's not connected in Circuit Lab. Once I have the connections, I can now go to a DC solver and add expression. Let's add V0, V1, V2, and V3, and then run DC solver. That'll tell me what the answer is. From the answer, I can now find the resistance. If I click on this wire right here, it tells me the current. That's 490 milliamps. 12 volts over 490 milliamps gives you the 24 ohms. Or equivalently, if I don't have this current, I know V0, 12 volts. I know V1, 2.19 volts. The difference, V0 minus V1 over 20, divided by, well, gives you 490 milliamps. Then from V equals IR, 12 volts over 490 milliamps gives you 24 ohms, which is the same thing that we calculated. In the lab, you would do the same thing. I would build the circuit, measure the current, and actually to measure the current, typically what you do is measure the voltage, then calculate the current. If I know the current coming out of the 12 volt source, I know the resistance that it sees, and I can see the resistance is 24 ohms. So that's resistors in series and parallel. And lecture number 3 for EE206, Circuits 1.